We're back at it, and this time we're going to take a look at models of the atom. So we're going to start building up, and we're really just going to be looking at nuclear structure here. But we've got a variety of different representations running from the very basic to very wrong, all the way up to much more advanced levels as we kind of move through this. So where does it all start? Well, it pretty much starts with Dalton's theory. And so what Dalton was looking at was attempting to build out structures based off of what he could observe. So we saw that we had these kind of larger structures and said, well, what could we do? Is it possible to break them apart? And what were those pieces that we could break them apart into? And we had very limited means, but we did have the ability to kind of break these things down. And what he ended up noting was that eventually you get a place where you can't break it down anymore. Okay? And those smallest pieces he deemed to be the atom. And that was his kind of theory or nomenclature that went with it. If we take a look at within that little black box, we're looking at roughly his periodic table. And when we're talking about his periodic table, what we're saying is that this part is his periodic table. And as we saw in the last video, we have 118 different elements that go into our periodic table. There's not 118 shapes in his periodic table. It was so small because we hadn't really found all those elements yet. Right? So this is what he had to work with. You'll also note the notation he's using is a little bit kind of different, more interesting. They're pictographic. So we're seeing these kind of random shapes and circles going through it. The circle was a pretty good place to start because we could look at building balls next to each other, and atoms kind of acted like spheres. So it made sense. The problem with that is that as you build larger and larger structures, and we're seeing a variety of different compounds down below, that the ability to draw those out becomes a bit cumbersome, to put it mildly. And that's why as we continued through our periodic table organization, we changed the symbology behind it. Right? So in Dalton's approach, he came up with kind of 5 principles. And it started with that an element was a tiny indivisible, not invisible for the record. There's a D in that word. Okay, indivisible, meaning it doesn't divide, and indestructible particles called atoms. Right, that was his theory. All atoms of an individual element are identical and have the exact same properties. Right? And that's because when he pulled from any different source, when he put those compounds together, you got the same results. Atoms of different compounds combine, or different elements combine to form compounds. So this is effectively the existence of H2O. If I take 2 hydrogens and an oxygen, I get H2O. Compounds contain atoms in small whole number ratios. So what we're referencing by those whole numbers is that we're seeing, well, whole numbers in there. We aren't saying decimals. We aren't going to see the compound H1/2O1. Okay, that doesn't exist. So we don't get fractional atoms. This is kind of a corollary back to Rule 1, because Rule 1 said indivisible, indestructible. Okay, so when they combined, you can only get whole number ratios. And then Rule 5, atoms can combine in more than one ratio. So in the case of H2O, I could take 2 hydrogens and 1 oxygen to make water, or I could make H2O2. Bad joke there. Feel free to look it up about water and H2O2. But what we're getting is different compounds that come out of that. So these are Dalton's 5 initial theories. These were not perfect. Okay? And in fact, his theories were very flawed, and we'll very quickly see some of the examples that break these. But that's a really good kind of test question moving forward. So it's probably a good idea to mark these 5 things and to know when and why they broke. Okay? So what was wrong about them. We move about 100 years later, and we get Thompson's model of the atom. So Thompson was able to discover smaller particles than atoms. He got electrons and thereby protons, because if you have this negatively charged species, you needed a positively charged particle to counteract it, because we don't see these charged things just free floating on their own. An electron has a relative charge of -1, and a proton has a relative charge of +1. So this is really just saying that the magnitude or the size of electrons and protons are the same, they're just the opposite direction. Okay? And he hasn't defined the charge, he just knows they're equal and opposite to each other. What I find interesting about Thompson's model, and why did we have to wait to late 1800? Why did we have to wait 100 years to get this advancement in science? So why was science dragging its feet so long? And really, it's kind of interesting. What it required was the existence of a vacuum. Okay? Vacuums are required to make these studies. The problem with just general testing of air is there's a ton of different particles in air, and so it's very difficult to see these subatomic or create these subatomic particles because they're so unstable. They will very quickly interact with anything that's around them. So what we had to do was create a vacuum. So with the invention of a vacuum, not the Henry vacuum clearly, but with the creation of a vacuum, we could create these tubes that have very little to no air in them. When we then pump electric current behind them, because we did have electricity, or we're studying electricity, we could see interesting phenomenon happen. For instance, we could see the tube start to glow. Okay? That in and of itself isn't a big deal, except that what Thomson also did was he started to place magnets around it, right? Because why not? You've got a magnet, you've got electricity, let's play with it. And so when he placed magnets near the tube, he noticed that that glow started to shift either towards or away from wherever the magnet was placed. And that thereby meant that we had to have a charged particle. Right? And that's kind of cool. We've got this existence of a charged particle, which meant that atoms were indeed divisible. We could break them apart and find those smaller pieces. But now that we have smaller pieces, we have to know how do we put those pieces together. And so this is where Thomson came up with his own model. So Thomson went through and said, okay, well, we do have these atoms. They have to be composed of these particles that we just discovered. Let's just start putting them together. Because if you take two north ends of a magnet and put them near each other, they repel away, said that we couldn't exactly have these things all perfectly in one space. Okay, so what he ended up saying was that the atom itself, that sphere, was just positive charge all the way around it. And that within that, we could eject these electrons. And that's how he could test and see his cathode ray. And so those electrons are now just kind of free floating in this sea of positive charge. And he likened this to the plum pudding that was popular at the time. So we've got a pudding that is the positive charge, and we have these negative plums that are now sitting within that pudding. And that was his model, and that's what he had. It kind of makes sense. We don't want those charges too close to each other. We need them kind of spread out, and we get a nice homogeneous system that would work to explain the models that we've seen, okay, which is kind of cool. Before we continue on with what our textbook has presented, I do want to mention this experiment just because I think it's kind of neat. Robert Millikan was the primary investigator, and Fletcher was the graduate student that was doing the work. Okay? And what Millikan was given credit for was determining the exact charge on one electron. That's kind of cool. So 1911. Why talk about this one? Well, there's a lot of kind of interesting stuff behind it. If we remember, Thomson didn't actually come up with the exact charge. He just said the relative charges, so positives and negatives, and that was it. So this left space for where Millikan and Fletcher could come in to define the exact charge. You do not need to know the exact charge, but it is specified there. That's the 1.5924 times 10 to the negative 19th C for Coulomb. Again, don't worry about it. Okay? What's neat about this is this experiment, okay, that was largely designed by Fletcher, and that's where this becomes interesting. So what did Fletcher do? So he took one of those little perfume aerosol-y things, and he filled it with varying substances, but eventually settled on oil being the most accurate for this experiment. And he would just aerosol, so spray oil everywhere. And if you've ever sprayed really anything, you'll notice that the liquid eventually falls. Well, these oil droplets are now a very fine mist, and he put them inside a closed container. And at the very bottom of that container was a little hole. Okay? And it was such a small hole that really you could only expect realistically at most one drop to ever fall through that hole. Okay? But that was the point, is spray this mist, get these tiny, tiny little droplets. As we're doing these droplets, that motion will remove some electrons and we get these particles to be partially charged. Okay? And that charged particle now floats downwards due to gravity through this tiny little hole. And then we got that little chamber, which you're seeing at the bottom of that screen. Okay, that chamber has a microscope aimed at it, and it's focused roughly where the hole is. So if something falls past there, you can see it. Okay, not a big deal. Okay, a drop fell by, not very useful. But he could at least see the droplet. The more interesting thing, okay, and that's what's being symbolized or written as a uniform electric field. And then this guy, that little symbol, is a symbol for, I believe, a capacitor. And so what that is saying is that there's now charge building on opposite ends of that plate. So as that particle, which is now negatively charged, floats downwards, the plates down here are going to be negatively charged. And because that one's negative, the other one must be positive. So now what happens? The negative particle floats down, sees a negative spot. Well, it doesn't like the negative, so what does it do? It repels away. So it will bounce upwards, right? Attracted to the positive plate. Right? And so then it could splash against the positive plate. Well, this is where our scientist, in this case Fletcher, looking at this microscope, sees the droplet fall through, spins the dial to adjust the electric field, so that what happens is that the electric field provides an upward force exactly opposite the downward force of gravity. Right? So what does that do for us? Well, what that does is that causes the droplet to float, right? Or exist perfectly in that single space. We could now, through the microscope and due to optics, know the size of the droplet because it's frozen in space effectively. We know the downward force from gravity. Since we know the size of the droplet and the mass through density, we now know the downward force, and we know that that is equal and opposite to the upward force from the electric field. Since we're controlling the electric field, we know how much electricity we're putting into that. What does that do for us? Through a system of equations, we could now solve for the exact charge on the electron. That's nuts, right? But that's not going to be easy, right? You're looking through a microscope, oil drop, electric charge, all these little bells and whistles that you got to spin, honk the little, perfumey thing. Stuff's going everywhere, right? So it's a big mess. So what do we need to do? We need to do this experiment lots of times, right? And lots. They varied the liquids. They ran it tons of times. And by they, I mean Fletcher. Right? So Fletcher ran all these experiments, designed it, set it up, was able to determine this charge. Remember, he's a graduate student. He took the results to Millikan. Millikan's like, these are fantastic. They publish them. Woohoo! Amazing. We know the charge on the electron. Nobel Prize comes around. Hey, good job, Millikan. Here's your Nobel Prize. Didn't Fletcher do all the work? Yeah, he did. But Millikan was the primary investigator, which means Millikan gets the credit. Right? And this is one of the things that's kind of sketchy within science. Primary investigators get all the kind of credit, and graduate students or postdocs work in those labs that are largely doing the work, don't get a whole lot of credit. What they do get is effectively street cred, which means when they leave the lab, they can get a job pretty much anywhere else, which was the case for Fletcher. So when Fletcher graduated, he could get any job he really wanted because he was associated with this Nobel Prize winning work. And within the field, nearly everyone acknowledges that Fletcher was the big brains behind this. And Millikan just happened to be in the right place at the right time. Not to say anything against Millikan. Millikan is still very, very, very smart person. Was very good at his science. But this particular experiment was largely driven by Fletcher. Right? So science primary investigator is the brain that finds the funding, finds the people, finds the equipment, finds the location so that science can take place. But because they're doing all of that big brain stuff, somebody else has to come in and act as their hands. And that's largely what happens within science. When you go to get a PhD, you would join a research group where somebody has done all of that legwork, and you then do projects that they tell you to do because they were the brains behind it. Under rare circumstances, in this case, Fletcher was pretty freaking genius level and came up with a lot of this on his own. Sometimes that happens, sometimes it doesn't. But that's largely what we do within science. So I think it's a neat thing to discuss because it's a really cool experiment. And it shows some of the kind of dynamics or politics within science. So again, big deal that you want to get out of this: Millikan, Fletcher, oil drop, charge on electron. Those of you being like, I'm trying to write down numbers, that's 4 things, 4 fingers, not 15924 times 10. I don't care about that. Millikan, Fletcher, oil drop, charge on electron. That's what you need, those 4 things. The rest is just history. We continue through our model for the atom, okay, and we encounter Rutherford. And Rutherford, also phenomenally interesting character, turned out to be one of Thomson's former students, and so took Thomson's work on the model of an atom and decided he wanted to develop and prove it. Right? So if we look at Thomson's plum pudding model, we get that nice little picture there. What Rutherford was able to do was acknowledged some radioactive research, and one of those radioactive sources is this thing known as alpha particles. And alpha particles are these relatively massive, positively charged radiation sources. And because they have that large mass, they tend to penetrate things, and that charge helps to contribute this. So if we take gold foil, a thin sheet of gold foil, we can see that light passes through. So these large alpha particles, we would expect the same thing. Okay, they should be passing straight through, because according to this model, there's nothing really solid there. It's just kind of this goo, if you will. So we take these alpha particles, we direct it at our gold foil, and what we would expect to see is it just to pass straight through, right? And so Rutherford famously described this experiment as aiming a shotgun at a piece of tissue paper, right? And watching what happens. And you probably haven't fired a shotgun before, but if you have, you would probably think that aiming it at a piece of tissue paper is just going to pass straight through. Like, okay, cool. And while that might seem like a boring experiment, it tells us that Thompson's model is true, because Thompson's model is just theory. We haven't proven it yet. So they go ahead and they fire it off, and holy monkeys, some of that buckshot came flying back at us. Hit the toilet paper, bounce back. That's not supposed to happen, right? And it's not easy to observe, and that's this experiment that they've got designed here. So if we go through and evaluate with the terms that we've labeled here, we've got our shotgun. Okay, we've got our TP, which has finally made it back to the stores. Not that I'm dating myself or anything. There's our toilet paper. And because this isn't a shotgun and this isn't toilet paper, these things are hard to see. We have this screen. Okay, so this fluorescent screen will glow when a particle hits it. We just see a little flash. And so what makes this experiment interesting is that they fired these things at this gold foil, and what they saw was that it hit behind the toilet paper. Go figure, it's supposed to go through. But the weird part was when it did this. Why on earth is that particle ricocheting to the left? Or, worst case, coming back at me. Okay. What kind of weird superhuman toilet paper is that? Okay. What it ultimately meant was that Thompson's model was wrong. And Rutherford had to go through and adjust and come up with a new way. Okay. Before we hit Rutherford's new model, though, I just have an interesting thought. What are alpha particles? Okay. And we did address it a little bit. They're these massive particles, okay, and they're positively charged. Right? Okay, where did I get them from? Well, they were a radioactive source. Okay? They come from a radioactive source. Well, where did I get the radioactive source? That is an interesting story. That bounces through history and largely falls at the feet of Madame Curie, or Mary Curie. Mary Curie is famously, or should just be famously, known for contributing a lot to the discovery of radioactive particles. Right? And her two big kind of discoveries are the discovery of radium and polonium. Right? And it's not just the discovery of them, it's the purification of them. And so she had to go through and dig through radioactive sources and sort out the different pieces that contributed one element versus another element. And radiation is really the atom falling apart. So as you're finding an atom, when it falls apart, it's now new atoms. So how do you sort all that out? And so that's pretty phenomenally cool. And so she gets a lot of credit for having done that discovery. But one of the things that I find more important, okay, and just to give you an idea, radium, we take a look at the radiation source that Rutherford used, it was radium, okay? Why I find Curie so fascinating and cool is the same reason why people have referenced Jonas Salk as being famous and cool if you're into virology or medicine stuff. When she discovered this, she's found like a pretty cool, amazing thing. She didn't patent it. Right? And what she did was helped people get access to these pure samples. And what that means is that when we go into Rutherford's experiment, Rutherford can trust that what he's getting out of that radiation source is this alpha particle beam, and that the results that he's seeing are due to alpha particles. Because if there's something else in there, we don't know why it's bouncing. Right? There could be another issue going on. So you have to control those variables. And because Curie was able to purify these things to now make sure it's one thing, that's amazing. Right? It's now even more amazing that she shared that with everybody else without charging an arm and a leg. Right? And that's to me awesome, because I am very anti-patent in that respect, because I think it slows science. But it is a complicated issue. Feel free to talk to business people if you're interested in that. Okay? But that was one of the reasons why we could advance through our models of the atom relatively quickly. We get vacuum, radiation, all these discoveries, and we know what an atom looks like. Another reason why I like bringing up Curie is that she's a woman. If we go through and reference all the scientists that we talk about, we're talking about largely white men. Okay? And so to have a woman contribute to this is amazing to be part of it. And it's not to say that people that aren't white men can't contribute. They can contribute, but they didn't have access to the same kind of equipment and tools and privileges that white men did, and that's why they could advance. So if you're interested in kind of hearing a rags, she didn't really get rags to riches, she was kind of rags to science goddess kind of level. Reading up on Madame Curie is a good idea because she's really neat. So how bad is it? This is someone that not quite single-handedly, but pretty huge contributions to overall science. Won the Nobel Prize. Cool, that happens every so often. People do that. She won 2 of them. She's one of only two people to have won Nobel Prizes, or two people to have won 2 Nobel Prizes. And extra cool, they were both in science. Right? She got 1 Nobel Prize in physics and 1 in chemistry. The other Nobel Prize person that got 2 Nobel Prizes, chemistry. Chemistry's cool. You get big bucks, big discoveries there. And what was it, peace? Like, I mean, come on. It's not even science. How hard can it be? So she's like the only person that has 2 Nobel Prizes in a science field. This is really cool. Last thing I'll throw in with Curie, she was denied access to the French National Academy of Sciences. 2 Nobel Prizes, and she wasn't allowed to be part of the boys' club of science in France because it was a boys' club. Yeah. So that whole kind of sexism thing really kind of detracted the ability for science to progress. If we look at Nobel Prizes, even her first Nobel Prize, they weren't going to give her. Like, there's some pretty serious politics behind a lot of this. So when we think about science and advancing, we should be trying to get access to more people because they can contribute a lot, but they have to be given that opportunity. So soapbox, I guess I'll put that away. Continue on. So Thompson's model doesn't work because particles did not pass through, or not all of them passed through. Some came flying back at us. Okay, so that's not very good. So what did Rutherford said? Said, well, we had to have a big, massive thing in our atom, right, which caused the alpha particles to bounce back. And it had to be tiny because most of the time the particles sailed through. So only some of the time did they bounce back. The other thing that we know about that big, massive thing is it's not just that it bounced back. If that thing was negatively charged, the alpha particle would have hit and stuck. We wouldn't see it. It wouldn't bounce back because that would be opposite charges. That's north to south end of the magnet. They stick. So that supermassive thing had to be positive, right? And he just kind of arbitrarily said that it made sense for it to be in the center of the atom, and that's where we're getting nucleus. So it is a nuclear model of the atom, and that's a pretty good start for atomic theory. But that meant he had to put all these positively charged particles into the same space. Not so good because they should repel away from each other. So Rutherford says, you know what, if we're going to do this, we're going to need some glue in there too. So we're going to invent a new particle that we haven't proven yet. We're going to call it a neutron. Neutron because it needs to be neutral so that it doesn't repel away from the positive charges and it holds it all together. Okay, so we now get a nucleus. We get our electrons on the outside, and then we get protons and neutrons in the middle of our nucleus, or the middle of our atom. Okay, give you an idea of scale. An atom is 10 to the minus 8 centimeters, and the nucleus is 10 to the minus 13. So 8, 13, not a big deal. 10 to the negative, that power thing, human brain doesn't do so great with. So let's make an analogy. Let's make the atom a superdome, so big superdome, right? The nucleus would be a marble within the superdome. That's like the tip of my pen. You're like, I can't even see it. I know. The tip of my pen in that little circle that you're looking at? Yep. Okay. The nucleus is tiny. Okay. Super, super, super tiny. That's kind of cool. So Rutherford said that we had to have these neutral particles because we didn't want the positive charges repelling away from each other. Okay. Chadwick, Rutherford's student, by the way, interesting, came back and was actually able to determine the existence of a neutron and experimentally proved it. Okay? And so now we end up with our 3 subatomic particles: electron, neutron, and proton. So in this red box, it's kind of the big summary of everything that we just talked about as far as the atomic model goes. And you're responsible for everything within that box. So this might be a good time to pause, make sure you copy all that down. Yep, still here, just checking. So how do we put this all together? So we have symbols that we covered in our first lecture. And now we have protons and neutrons, okay, and technically electrons, so we're going to address that. So we encounter what's known as atomic notation. I have a huge problem with this. It's not atomic notation. Because atomic notation means that we should be looking at all the particles, and we aren't. What this is actually referencing is nuclear notation. So in a little bit, after we cover nuclear notation, we'll make it atomic by showing where the electrons are. So nuclear notation, we start with a symbol. Right? In this case, we're picking SY because those are the first two letters of symbol. And if you've been studying your elements, you'll notice that that's a pretty common pattern. And then we reference a mass number and an atomic number. Right? The mass number is written in the upper left-hand corner. Because we're an English-speaking society and developing a lot of this, we placed it up in the upper left-hand corner because that was the first thing that we were going to read. Right? Because we read left to right, top to bottom. So that's our first reading thing. And that's going to become important here in a second for understanding why we're placing these things where we are. Okay. Then we get the Z, okay, which is at the bottom. Okay. So if we're reading left to right, what we're probably doing is going that first thing. Then we see the symbol as our second. And then we see that Z as our third and last thing to read. Right? Why is that important to us? Well, that's really going to come down to why do we care about this notation? Why are we using it? Right? I said it's a nuclear notation because what we're looking at, if you look at all the symbols on this, is we're only looking at the protons and the neutrons. Well, protons and neutrons are only found in the nucleus. Right? So that's why it's nuclear notation. Right? Why do I care about looking at the mass number first? Okay. Well, the mass number is the sum of the protons and neutrons. So we would add all of those things up. Okay. And it turns out that if we have enough protons and neutrons, so if we start getting into mass numbers that are, I think, greater than, not positive on my radioactive ones, but I think greater than 90-ish. I don't remember exactly. But let's just stick with that. Greater than 90-ish. Our nucleus starts to become unstable and it starts to fall apart and we get nuclear radiation. Right? So why do I want to see that number first? Well, if I told you that there was a nuclear radioactive source behind you, are you going to freak out a little bit? Probably, maybe just a little bit. Right? Nuclear bombs, danger, right? Okay. Nuclear power plants, oh, I don't want that in my backyard. Okay. We freak out at that. So what we want to be able to do is see that information first. So the first thing I'm going to encounter is going to be the thing that's going to trigger, is that radioactive or not? Right? That radioactivity is our mass number. It's very important to see that. So we start with that. And that's our protons plus our neutrons. Again, nuclear notation. The second thing we read, because we read left to right, would then be the symbol. Right? And so we would then be able to see the symbol, we could look at the periodic table, we could find the symbol, and as soon as we found that, we would know the number of protons. We haven't talked about it specifically yet, but that's coded in the periodic table very quickly. So if I know the symbol, I know the number of protons. Well, if I know the number of protons by looking at a periodic table, because I'm a chemist, do I need to write the atomic number? Isn't that a bit redundant? Yeah, I would argue it is. Right? And so the atomic number becomes something that's a little bit not useful to write because the symbol has already given us that information. So why would we want to include it then? Okay, well, one of the reasons we might want to include it has to do with how we would interpret some of this information. Right? Figuring out the number of protons, useful, quick, easy. But the number of neutrons, I have to run a calculation. I would have to subtract the number of protons from the mass number. Right? So I would take my mass number, and if I was, write this out longhand because, math, and our protons subtract, and then I would have to get my number of neutrons, right? Right? That's close enough to spelling neutrons. So I would have the mass number above, the protons underneath. Holy monkeys. Isn't that exactly what this notation shows? It does. Okay. So if I have that notation written out, all I've got to do is now write out and do the math and come up with whatever my number is down here. And I now know the number of neutrons relatively quickly. My notation sets this up so that I can do the longhand math for solving for the number of neutrons without having to pull out a calculator. Is that why it's set up that way? I don't know, but it works. So take advantage of it. Okay. And we've got our nuclear notation. So one of the things that I did call out right at the beginning was that we're calling this atomic notation. I said that's a bit misleading because for it to be atomic notation, we would need to know the rest of the atomic structure. And atomic structure is protons, neutrons, and electrons. Well, where are the electrons? If we take a look at our system, we've got the upper left-hand corner identified with our mass number. We have our atomic number in the lower left-hand corner. Have we seen anything written for our lower right-hand corner before? Oh yeah, we have seen, okay? In that lower right-hand corner would be the number of that element, okay? Or the quantity. Let's stick with quantity, I like that better. Okay, of the atom. So that's taken. What about the upper right-hand corner? Well, right now we haven't specified anything there. Guess what we're going to put in that corner? We're going to put information about our electrons. Okay? And similar to our mass number was something that didn't explicitly give us our neutrons. We had to calculate it. That upper right-hand corner is going to be charge. Okay? So that charge is going to come from the number of charged particles in our atom. Okay, so we know the charged particles would be protons and electrons, which means our charge is going to be our protons plus our electrons. Okay? And where we have to remember is that our electrons are negatively charged. So really what we're saying is a positive 1 charge on the proton times the number of the protons plus the negative 1 charge on an electron times the number of electrons. Okay, and we've got it. Or if you want to try and memorize another formula, you could go through and say protons minus electrons, and that gives us our charge. Okay, and we now have a way to relate that. Most compounds that we'll look at will have 0 charge, but we will encounter a unit where the charge is going to become very challenging, and that's usually the next unit, okay, unit 2. If we simplify everything and clear it all away, when we're looking at our atomic notation, very commonly, we do not see anything written in the upper right-hand corner because the charge is 0, which means the protons and electrons exactly cancel out. And that's why we're not seeing a charge show up there. Okay? And that's why the textbook has decided not to reference it, and why most things don't reference it. But if we're going to look at atomic notation, you should remember that that upper right-hand corner has charge, and that has to do with our protons and our neutrons. Or sorry, protons and our electrons. Okay? So with that, let's go ahead and take a look at some quick examples. So using our atomic notation, if we're given the example as shown, you should be able to tell me what the element is, the atomic number, mass number, and your number of neutrons. So this is a good opportunity for little quiz questions. So I'm going to go ahead and give you a second to do that. And as we go through and look at this, the element we should know because we're required to know that Si is the symbol for silicon. The atomic number found in that lower left-hand corner is a pretty straightforward one with 14 protons. The mass number is in our upper right-hand corner, or sorry, upper left-hand corner. And we know that we have 29 which is the number of protons and neutrons. Since we now know the number of protons and neutrons, we can solve for the number of neutrons. And our work for this, we could write out P plus N, subtract P from both sides. N is 29 minus P. I said P was 14, and I would get 15 neutrons. Okay, and so there's our atomic notation. Pretty slick, okay? Here's our big summary thing that has all of those pieces. I want you to go through and consider these processes and being able to come through and label each of these things. That meaning category is a tricky one, and so I'm going to reveal that information in a later video in the hopes that you spend some time trying to figure out what that means. To help you with that meaning, I would argue you should start with protons, and then you could look at electrons, and then you could look at neutrons. So first, define what protons mean. So if I say 6 protons, what does that mean? Okay. Once you've defined protons, then say, what does it mean if I have 5 electrons with those 6 protons? What does that mean? What does it mean if I now say I also have 6 neutrons? Okay, what does that mean? That's getting to the underlying idea behind these, not just the raw facts, and that becomes an important aspect to do. And with that, I think the next little section is going to talk about isotopes. Come on, the devices are not working with me. Yep. So I'm going to backtrack because the isotopes one is a challenging one, has some challenging concepts, so I'll make that in a new video. So with that, we'll go ahead and say thanks for watching, and we'll see you in a few.